So previously we calculated the one based on iron. So you can verify that by calculating based on iron before the endpoint and match the one for serial. Okay, so again, this whole picture looks messy, but then if you look at line by line, it's really neat. Okay, previous examples, they were based on one-to-one. Those are easy, right? So now non-one-to-one to confuse you, but the idea behind is the same. So for example, this particular reaction, so you're going to have to balance the equation by doing the two-half reaction combination, right? By knowing the number of electron transfer, then you can balance for this overall reaction. So keeping in mind the number with arrow, okay? I'm pointing at the 5, pointing at the 8, pointing at the 5 again. So you need to take those into consideration. Okay, then this is your titrant solution. So the acid, this H2SO4, and then 0.5 molar for H2SO4, this chemical. So if you look at the H only, single H, then it's going to be 1.0 molar, okay? So read a problem carefully. So in this one is 0.5 for H2SO4 in the titrant solution, okay? So let's say the condition is you have added 10 ml of the 0.0200 molar permanganate. So the 10 ml has included the H2SO4 together as one solution. And this is your substance of interest. So your analyte, you have 100 ml. Let's say this is standardization, 100 ml upon 1. So 10 ml of that is added. So here now is a step calculation for you. Titrant added. So first of all, you need to calculate the total millimoles of your analyte available. Okay, the Fe2 plus. So this absolute total has nothing to do with coefficient yet. It's not for reaction, but just the total. If you go to MV, so you go to 10 millimoles. Now 10 mils of your titrant added. Okay, 10 mils. So the MV is equal to 0.2. So now you relate the two quantities. You realize this is before the endpoint, right? It can easily be seen. It is before the endpoint, right? So do you have any difficulty to see it is before the endpoint? Yeah. Okay. Jeffrey, you have difficulty to see? Really?
Oh, no, not anymore. I see it.
Oh, okay. Because a large excess quantity, right? You have 10 millimoles here, you have only 0.2 millimoles added, right? Okay, so this is before the endpoint. So you are asked to calculate the potential of the mixture. So you're going to use the iron, right? What we learned previously. So based on the iron. Now set up the Nernst equation. Okay, the N. This is based on the particular half reaction, so the N is for the half reaction. Be careful, it's not the common. Then you log, right, the ratio of these two species. So now it's a matter of plug in the quantity. So this represents how much is left, right? So how much is left, right here, how much is left is equal to, initially you have 10. Total. So start with the total. Subtract the quantity reacted. coefficiently with the manganese, the permanganate. So it's 5, notice, it's 5 to 1. For 1, then 5 of that reacted. So here you have added 0.2. So 5 times as much it will be reacted. Right? So I go the shortcut because I trust what you learn in 1B, right? We don't need to do the dimensional kind of deal. So as you can see, right? So if subtract 5 times of that, so this is the quantity left at equilibrium at this point. Do you have any problem to see that? Okay, so this is checked. Then what about the Fe3 plus? So Fe3 plus is your product. After adding the titrant, then this is what you're going to generate. So generate it coefficiently with the permanganate. So exercise your logical thinking. So here is the quantity, the absolute quantity added. Okay, so permanganate is 1 to 5. So 1 going to generate 5. 1 mole going to generate 5 mole. So that many mole going to generate 5 times as many moles for the Fe3 plus, right? So now you get 9 over 1. Absolute number of moles, concentration is over a volume. But then notice it's ratio. So the volume divided by whatever the volume is, this is divided by the same volume, so they cancel each other. So you don't need to consider the volume, simply the absolute number of moles and plug in, and this is what you calculate for that particular point. Any question? Okay. Now, after 100 mils of the titrant, so this is going to be tricky. Okay, so 100 mil mV of the titrant. You're going to have that many millimoles added. Then the initial quantity is the mV initial quantity for the 2 plus, Fe2 plus, equal to 10 millimoles of that. Then notice when you add 2 millimoles, then it's exactly going to react with 10 millimoles, right? So this indicates it's at the end point, right? So once they match the ratio of 1 to 5, then this is exactly reacted. So this is at the end point. And now you're going to use the endpoint formula to calculate the potential. Okay, so that's been proven, so you can use this confidently. So for AB, 2 chemicals. Now, how do you treat the proton? Well, the proton is on the left, and therefore is plus. Okay, what about the N here? The N is common N. Okay, which is the 5. The common N is the 5. Then proton concentration to the exponent 8. Okay, next we will look into the values to plug in. Okay, even this guy is tricky. Even the H plus quantity is tricky. But so far, do you have any question, particularly the relationship here?
So like real application would be
Real application.
like battery. It's kind of the same concept.
You will not use
Well, yeah.
manganate.
Yeah,
But we will learn that. Good question. We'll do electrochem a little bit more later. Okay. Now, here the n plus, the two n values add together equal to 6. 1 plus 5 is 6. Okay, so 1 plus 5. Yet that 5 is a common, the factor, the common factor, highest common factor is 5, is not the 6. Okay, now the concentration is not your piece of cake of 1 to plug in concentration. It is a magic number 0.42, but it is not magic. After all, if you involve the calculation more carefully. Now remember, the 0.5 molar stands for H2SO4. Okay, if you break it into H only, then it's 2 times that. Then multiply the volume, then this is your total number millimoles of proton. We are talking about the proton here, so this is the total number millimoles of proton added along with your titrant. Okay? Any question with this? Because you add a 100 mil, so this is what being carried simultaneously into it. So this is the absolute total. Now that concentration is whatever left at equilibrium, right? So the left quantity is equal to whatever the quantity, total quantity added, subtract the quantity reacted. So remember, the coefficient was 8 to 5 of the Fe2 plus. Okay, so 8 to 5. So this is Fe2 plus total being 10 millimoles. So when this is totally reacted, then correspondingly is 8/5 of proton reacted. So this is a proton reacted. Yes?
Why 8 to 5 and not 8 to 1? Why do we use the iron?
It's reaction between, because the permanganate is not,
Oh, right. Okay.
it's not proton reacting with permanganate. It's a proton reacting simultaneously, with
Got
the Fe2 plus. Yeah, good question. Yes?
The 2, did you say that was because there was 2 protons in H2SO4?
H2, right? Yeah. 0.5 molar stands for H2SO4. Okay, so dilution. Okay, this is the absolute number of moles over the volume. Now it's 100 mil sample, 100 mils titrant. So it's 200. That's how you end up with the magic number. Okay? And now you end up with that at the end point, and you do this. Any question?